Hi guys, and welcome to Physics 4B. Today is Wednesday, April 28th. We are basically finishing problems with chapter 28, and as promised, I think we're going to touch a little bit on also problems from chapter 27. Basically, only one application or two from that chapter in here, actually in this book. So I'm looking at the problems that we're going to be doing today. The lab, I think we're going to meet at 2 o'clock. I already posted the lab instructions for you guys. There is a component in it that is basically, that we have to scratch, and that is to do with the building the motor in it. But everything else should be done. Okay. The instructions are actually on Canvas, and we're going to go briefly through it in the afternoon. So hopefully you guys will join, and so that you complete your lab. It's due next week. Okay. So that is in terms of the what's going on in the afternoon. And also, did you guys receive a message from the dean pertaining to the NASA basically project?
Sorry, what was the question? I caught up really quick.
Did you guys receive an email from the dean?
Yes, I did.
Jason? And also I forwarded it today, so it's the same thing. So I'm hoping that you guys will take that seriously and hopefully have some fun in the process and actually take advantage of what is offered there. Good? Yes? Or no?
Sounds good.
Okay.
I'm definitely excited for it.
Okay, very good. I look forward to have people on it so that we can get things done. Okay, the deadline for that is coming soon. Okay, so it's early next week. So hopefully you guys will take care of that this weekend. Anyway, so let me share with you the screen, the problems that we want to do. Share. Okay. And this is basically chapter 28. Where is my pen? Okay. So chapter 28, the first problem that I thought we will do, so we're still doing chapter 28, so that's your the first problem we're going to do is problem 38. Okay, and that's on page 948. Okay, a word of caution. And I know I said that before in the past, but now it's worth reminding you guys again of it, okay? I know for the few who sits in the other class also, for C, I mentioned that earlier in the day, so it's just another reminder. Physics is about doing. It's about doing these problems. Oh man, somebody on the side was excited with this motorcycle. Sorry about that. Anyway, you have to pick up a piece of paper now, if you didn't already do that, and a pen or a pencil, and start working this very same problems. Piece of paper probably will not be enough, so you need a lot, okay, to do actually things. You cannot watch me do things and expect to learn anything from this class. The lecture is fine. You're going to go through it. I mean, think about what we do in the lecture, probably take some notes in it. But it's by far, the problems that we do together are the ones that are very important, that you guys will reinforce what you learn in lecture and make you actually, will enable you to learn these things, okay? So if you don't do that, you are really shooting yourself in the foot. So I'm sorry to say that, but basically you're wasting your time, and I really don't want to see you waste your time. So grab a piece of paper, grab a pen or a pencil, and let's get these problems work together. So while we're doing that, look for 6 things at the same time going on through each and every one of these problems. The first one, we read through the problem, we try to understand what's given in the problem, we see what's asked in the problem. Then, step number 2, get all the relationships that we need, whether from physics, geometry, or whatever other things that are related to that. Trig identities, integrals, whatever is needed to help us do this. So that's step number 2. Step number 3 is actually solve the equations, whether algebraic equations or non-algebraic equations, integrals, or whatever we have to do, and justify the steps. So those are 2 steps in the same thing. So we cannot really go from one step to the next without really full justification and understanding what that's from one step to the next until we get to the bottom line. namely answering the question, finding the solution, and then check to see if it makes sense and have a general discussion. Because here is the deal. If I tell you today we're going to do problem 38, followed by problem 61 and 62 and 63, I'm sorry, 62, 61 and 62, and then 67 and 63 in this order. And if we have time, we're going to go to problem 49. And if you just watch me do these things, yes, you may understand what I'm doing while I'm doing it because it makes sense to you. But if you don't actually do these things and go through the steps yourself, you're not going to, first of all, remember or know or learn anything from them. So it is very, very important that you guys do these things, okay? Write them and go through them. Because I can even tell you, okay, you know what, here are the problems that we're going to be doing, and go research them, and you could. There are all kinds of resources where you can go and find the solution. And all you have to do is just copy the solution. And if you don't have time, just basically scan it on a scanner and send it. Here is the solution. Ask me to provide you a solution. Here is a solution to these problems. But that is useless. You have to really go through the steps, because most of the solutions, they don't go through these things. It has to go through these things. You have to understand what the problem is asking, what the problem is giving. You have to understand what needs to be done to solve this problem. You have to actually solve the problem and justify the steps, and then think about the solution. Once you do that, I guarantee you, if I give you a similar problem like this one in any exam, you should be able to get it through. I mean, to go through it with the flying colors, with no problem whatsoever. That is the reason why I do these things. And that's what I hope you guys will do also, for you to learn these things. You saw the theory, you saw the lecture, and the lecture may have a lot of things in it, and but it's kind of dry, it's kind of up in the, I mean, it's in the clouds like this. But with these problems, it brings into focus and makes it make sense. So that is what I'm hoping that you guys would do. Now, here is a question for you guys. Does everybody have a papers and a pen and a pencil so that we can get going? Okay, this one person, Elizabeth, is ready. Is everybody else is ready too? Okay, 2 people are ready. Great.
Ready.
Okay, very good. Sarah also is ready. Okay, Montserrat. So I have more people who are ready to do these things. Okay. If you don't have the book ready with you, I can read the problem, but that's fine. We can solve the problem together. And if you don't think that something makes sense, we're going to stop through it and do it together. Okay, so let me share with you again. So the problems I was going to do from chapter 28 are the following. Again, problem 38. If you look at problem 38, it rings a bell big time. It is actually problem number 1 from the exam, except that problem number 1 from the midterm was dealing with charges and Gauss's law. This problem deals with electric currents and actually Ampere's law. So it's identical, with the exception that the laws are different, the verbiage is probably different, and everything else is slightly different, but it is identical in terms of the solution. Okay. The second problem I thought we should do is problem 61. Problem 61 was last semester an exam in one of the exams that I administered last time. Okay, similar to it, of course. Okay, problem 62. Problem 62 is similar if you look at the problems to problem 64. Problem 64 also was in an exam last semester. The only difference between them is one of them actually is a half circle shape for the other one. The other one is actually 120 degrees, slightly bigger. Okay, so they're actually they are very similar to problem 62 and 64. However, we're not going to do problem 64. The next problem is actually 67. Problem 67 is very similar to a lot of problems we did actually in electricity too. Okay, except there we had a charge distribution. Here we have a current distribution. That's the difference. Problem 63 in this order. Okay, I know you're saying what happened 62, 60, 61, 62, 67, and 63. Yes, I'm trying to stick to this order. And then We're going to go to problem 49 at the end, provided we have enough time to go through all of them. Some of them I probably will do it thoroughly. Others, I'm going to ask you to complete them or finish them and give you all of the, basically the ideas for them so that you can complete them. Okay, so problem 38. Problem 38, step 1, so that we are all on the same method. We're going to read the problem, okay? It tells you a figure 2838. So let me draw the figure, since that's the first thing that is asking for us to do. So the figure has an I1 current going into the screen, okay? Has an I2 current coming out of the screen, and has an I3 current also coming out of the screen, okay? And it has a contour it has a contour A first, so this is contour A, then B, and then C. It's like a path, basically. And finally, contour D, which everything is in it. You probably have guessed what we're going to do. I'm sorry, contour D. We're supposed to find the circulation of the magnetic field through each and every one of these contours, A, B, C, and D, okay? So without even reading the remainder of the question, if we just saw the lecture, it's probably that's what we're headed with this question, okay? So figure 2838 shows in cross-section several conductors. So these are wires that are going all the way to the screen or coming out of the screen, depending on which one they are. And we're looking at them on this side in here, okay? We're cutting them. So basically you take scissors and you cut them through and you're looking at their cross-section. So this is not, the wire is extending to infinity both ways. And this cut is a mathematical cut, not a real cut. If you cut it really, you're not going to have a current flowing. So the current I1 and I2 and I3 will be 0, okay? So through the plane, the currents are given. I1 is 4 amps. There are 2 sig figs in here, okay? I2, so I'm already in step 2. I'm taking the data that was given in this problem, okay? 6 amps. And I3 is 2 amps. Okay, so that's given. And the directions are shown. I1 is going to the screen. I2 and I3 are coming out of the screen. Okay. And 4 paths labeled A through D are shown. What is the line integral of this line integral, basically, which is circulation? That's how we define it. Of BDL. The units for this one, the units for B is Tesla. The units for the distance is meter. So the units for this quantity, the circulation, is going Tesla by Tesla meter. Circulation. So I want to find the circulation. Okay. What is the line to each? So each integral. So basically, trying to find this one through all of these paths. So we need to calculate this line integral through path A, path B, path C, and path D. The worst thing that we should probably do is actually calculate this thing. We're not going to calculate B and plug in the value and start to go through. They didn't even give us what these paths look like. They gave us shapes, and I drew them in here in arbitrary shapes. They're not necessarily circles. So they could be any complicated shape that you have in there. The point being in here is we're invoking something we know, namely Ampere's law. So Ampere's law says that this circulation along any path that you wish is the mu naught times the sum of the enclosed currents by the paths. Okay, so that's it. So this is the deal then. Let's find it for path A. So this circulation through path A is BDL and it's mu naught times the sum of the currents enclosed by path A. Look at path A. How many currents are enclosed?
Nothing?
None. So we have 0. So we have mu naught times 0. So this value is 0. It's very simple. Okay. So this is similar to the exam stuff, except there we were dealing with Gauss's law. Path B. Now I have to be careful, okay, with the signs, because path B, the right-hand rule says we're circulating always in the counterclockwise. So these circulations are all of them counterclockwise. But the magnetic field, actually, because the current is going in, so the magnetic field must be clockwise. So the magnetic field due to I1 is in this direction, okay? And we're circulating in the positive direction, so this has to be a negative value, that's all. So it's minus 4 amps times mu naught. And that is the current enclosed. We're only enclosing I1. So for path B, this circulation, again, we don't really do this integral in here at all. That's the whole point of Ampere's law, so that you don't do it. The whole point of it, you write it, but you don't really carry that integration, okay? So this is Ampere's law, by the way. So I'm justifying everything while we're writing. So we're going through the steps. So in here, the current enclosed is only minus I1, okay? And the reason why it's minus is because it's coming out of, going to the screen. Okay? So this one is equal to minus mu naught times the current, and the current is actually 4 amps. 4 amps. So it's minus mu naught times 4, and mu naught now, I need the value of mu naught, which is 4 pi times 10 to the negative 7. 4 times 4 is 16 times pi. So I need the calculator in here. 16 pi. And the answer is 50.265482. I mean, I need how many sig figs in this problem? 2 sig figs. Okay. 2 sig figs. So it's 50 with a negative. I'm sorry, I need to multiply that in here. So the circulation again for path B, dl, is going to be equal to minus, because of the minus sign, 50 times 10 to the negative 7, or negative 5.0 times 10 to the negative 6 Tesla meter. That's easy, okay? Now, we do the same thing. For path C, though, I have to be careful now. Path C. I have the circulation of this stuff in here, of BDL, is going to be equal to mu naught times. I have I1 going in, and I have I2 coming out. Yes? So I have a negative 4 and positive 6 amps for a total of a 2, positive 2 mu naught. Okay? Make sense so far? So this will be, instead of 16 pi, it's going to be 8 pi, and 8 pi, very good, and 8 pi will be just half this number, whatever that number is. So it's going to be minus 2.5. Oh, I'm sorry, positive 2.5 times 10 to the negative 6 Tesla meter. Okay? And then for path D, which is all of this path basically together. So path D, it's going to be BDL mu naught times the sum of all of the currents, which is negative 4 plus 6 and plus 2. So it's going to be negative 4 plus 8, which is positive 4. So it's 4 mu naught. So it's going to be a positive 50 point, I'm sorry, negative 5.0 times 10 to the negative 7 to the negative 6, I'm sorry, Tesla meter. Okay, I just basically, I didn't do the actual calculation, just I'm relying that this one is correct. So hopefully you guys can check this numbers in here and verify them for me. The point being in here is, that you can use Gauss's law, I mean, not Gauss's law, Ampere's law to do these calculations, okay? There is not a lot of discussions really to happen here. The only thing is, this is a direct implementation of Ampere's law, okay? So this is straight out of the of basically taking it's just like a substitution, basically direct substitution. And here, the only thing in here is that you have to be careful with the numbers in here, okay? Because the magnetic field is usually of the order of mu naught. It's a very small number. So this is actually typical value in here. So I'm not alarmed. So if I see somebody, for example, having, instead of multiplying by 10 to the negative 7, they by mistake they divide by it, and then they will have a huge magnetic field of the order of 1,000,000 Teslas. That is ridiculously big. I mean, 1,000,000 Teslas is of the order of a neutron star. So nothing can stay next to that magnetic field, okay? So it's a huge magnetic field. So just, this is a typical value. So this is if you want to add it to the discussion. So this is easy enough, isn't it? Especially in light of the midterm that we just had. Good. Makes sense?
Yeah, can you scroll up a little bit? Yeah, right there.
Okay. The biggest, no problem. The biggest deal in here is the signs. You have to pay attention to your signs. That is the biggest problem in here when it comes to this issue. You have to know which signs they are, okay? The circulation is by convention always taken in counterclockwise, okay? So this is correct here. So this one current is going in. So the magnetic field, according to the right-hand rule, should be circulating clockwise. And since the circulation is counterclockwise, the contribution to the circulation coming from this current is negative. That's all. Okay. Everything else is positive because the currents are coming out of it. And here there is no current enclosed through path A. Okay. So that takes care of that. So let's look at problem 61. Problem 61 actually takes you back to a little bit of mechanics from physics 4A. So problem 61, what you have in here, you have, let's read the problem first. It says 2 long parallel wires hang by 4 centimeter long cords. So you have two wires that are basically attached by 4 centimeters. They're very long, okay? You attach them by 4 centimeter long, 4 centimeter wires, okay? And then the wires have a mass per unit length of, so the length of the wire, not the length of the cord. You have to pay attention to this length in here because sometimes this is where the confusion comes in. When you have two variables for because when we talk about the wire, we also talk about its length too. But we're not talking about the length of the wire. We're talking about the length of the cord that suspends it, okay? So this length is 4 centimeters, 4 centimeters. You have 3 sig figs in this problem, okay? So let's keep tab of that. From a common axis, the wires have a mass per unit length of this much. So the wires, not the cord, the wires, mass per unit length. I don't know if you use the letter mu or not for it, but that's how sometimes it's referred to, is 0.0125 kilograms per meter, okay? So that's how much these wires weigh for each meter. Obviously, if I bring a meter, the meter will weigh about 12.5 grams. If I bring the kilometer of that, it's gonna weigh what? 12, you multiply that by 1,000, okay? no, a meter. Yeah. So it's going to be so it's going to be my times 1,000. So it's going to be what? 12.5 kilograms. Yes. So the longer you have of this wire, the more it's going to weigh, basically. That's it. So that's what that means. Okay. What is the current in each wire if the cords hang at an angle of 6 degrees? If you look at the shape, let me first of all draw the shape because it's very important. Okay. So we have the wire 1 and we have wire 2, and both of them are suspended by identical wires from a common place in here. So this current, if you look at it, is going in this direction I, and it's opposite in here in the other direction I. Because the currents are going in opposite directions, the wires will repel one another. Remember, in the case of magnetism, when currents go in the same direction, they will attract. When currents are going in the opposite direction, they will repel. Okay, and we found the formula for it too. Actually, we did it last time, and actually from chapter 28. What is currents? Try to go through the notes that we did last time. Yeah, here are the 2 wires, okay? And we found that one wire will be subject to a force that is proportional to mu naught times the product of the 2 currents divided by 2 pi times d times, this is the force per unit length. And if we want the actual wire, we have to multiply it by L to get the actual length of the force. So we're going to use that expression in here for this problem. And now we're actually suspending it actually from another side too. So what they're saying in here is this angle, they gave us this angle in here. This is the vertical, by the way. This angle is equal to 6 degrees. So on both sides, it's 6 degrees, okay? So it opens by 12 degrees, the 2 wires. Because you have currents, if they kill the current in one of them or both of them, they should repose back. They should go back, relax back to their position. But now, since there is a current, they're actually repelling one another. So look at it from this perspective. So I'm going to come in here and look at one of the wires, this one, for example. Okay, doesn't matter which one I'm going to look at. So I'm going to look into one of the wires. So the current is actually going into the screen in here. So I'm going to look at it here, is how the current is going. It's going into the screen. So this is the vertical. And this is being suspended by this cord of 4 centimeter long. So this is 4 centimeter. This angle is actually 6 degrees, and this is the vertical. Its own weight is mg. The tension in here, I'm going to call it T. And the force of repulsion due to this magnetostatic force is F. So this force due to the magnetism, this is mg, and this is the tension. Okay. And now we have a statics problem from physics 4a. So we want to say that the sum of the forces, namely F plus mg plus T, must be equal to 0 if this force, if this string is supposed to stay in its place and not go anywhere. So what I'm going to do to this expression, I'm going to project it in the x-axis. I'm going to project it in the y-axis and make sure that the components in here cancel mutually in both directions. So in the x-axis, so basically now we have all of the things we need. I'm going to call this angle theta if you like, but we have all of the information. We read the problem, we understand it, and they want us to find the current, by the way, I, that makes this happen. Because if you don't have current, this separation cannot happen. So you have to have a current to separate the 2 of them, and the current needs to be going in opposite directions. And that's basically how this one was repelled back by this this magnetic force in here. So magnetostatic force in here depends on the length of the wire that we're going to write. So the magnitude of this force is actually equal to mu naught times the first current times the second current. It's the same current, so it's I squared, by the way. Okay, times the length of the wire divided by Go back into that expression that we did yesterday, not yesterday, the other day, 2 pi times d. 2 pi times the distance between them. So I need to know the distance between the two wires, 2 times the distance between the wires. I need to know this distance. If I know that distance, this is just half the distance because the other wire is actually sitting on the other side, halfway in the opposite direction. So this is just half the distance. If I can find half the distance, I multiply it by 2, and now I have found the full distance. I know this is 4 centimeters. I know this is 6 degrees. So I know that half the distance divided by the 4 centimeters is going to be the sine of 6 degrees. From here, I can find that this distance is equal to 2 times 4 times sine of 6 degrees. If I do this math, I have 8 times sine of 6 degrees. That should be my distance in centimeter. And I will need it probably in meters if I want to have this force in Newton. Okay. So there is a warranted in here conversion that we have to do for this, because this answer is going to be in centimeters because this guy is in centimeters. Okay. So let's work with the algebra first. So we have F in this ax system, it's a negative F. So it's in the negative F direction. This has a 0 projection, and this is positive. It's T times, it's the opposite to this angle theta. So it's T times sine of 6 degrees, because this angle also is 6 degrees, equals to 0. But I don't know what T is, because F depends on I squared. So if I can find what the tension is, then I'm in business. I can find I squared, because I was not given to me. So I is unknown. And this is what we want to find, is the current I. Because if we find it, we're in business. So the other expression then in the y-axis should be the other one to help us find the answer. In the y-axis, F has no component, so it's a 0 component. Mg is actually negative, so I will have 0 minus mg plus. Now the tension is positive. The components of the tension are positive, and it's actually the adjacent to the 6 degrees. So it's going to be T times a cosine of 6 degrees, and this must be equal to 0. So this is equation 1, this is equation 2, and now we should be able to solve. Let's see if we can find stuff. So if I take equation 1, rewrite equation 1 as follows. F, I'm going to move it to the other side, will be simply T times sine of 6 degrees. And the second equation, if I put mg to the other side, it will be mg equals to T times cosine of 6 degrees. And if I take this equation, so this is just equation 1 basically rewritten, and this is just equation 2 rewritten. So if I'm going to take the ratio of the two, then I get rid of the t, because I don't know t and I'm not asked to find it, so I don't care for it. So on one side, it's going to be tangent of 6 degrees. On the other side, it's going to be F over mg. Okay. I don't know what the mass either is. They didn't give me the mass of the wire because they didn't give me the length of the wire. So what I'm saying in here is take any portion of the length. So this is actually not for the entire. So this is just this portion. It doesn't matter how much it is. So if it's length L, if it's under length L, that one is going to be subject to the same force that has the same L in it, because that is the force on that portion of the string, portion of the wire whose size is L. So for a segment of length L, the force first is given by mu naught times I squared divided by 2 pi times d times L, because this force is per unit length. Now I need to multiply it by the length to find the actual force. But m in that case is equal to mu times L for that same segment. So having said that, then I'm going to sub into this expression and I should be able to find the answer now. So mu naught I squared times L divided by 2 pi d, that is the force in the numerator, divided by mg, and mg is mu times L times g. And this is good because the L cancels. This is equal to tangent of 6 degrees, by the way. Okay. So this is good because the L cancels now. That's very important because they never gave us L. So this is true for every tiny segment of the wire, this relationship, no matter how big L is. So if you take a mile long of a wire, that's fine. If you take 50 centimeters long, that's the same relationship, it doesn't matter. So the condition of the current is the same. So if we solve for the current, we're going to multiply by 2 pi d and divide it by mu naught. Don't forget the g in here in the numerator. So it's going to give me, under the square root, it's going to give me a value for the current, I, equal to the square root of, first of all, the tangent, I'm going to write it at the end, tangent of 6 degrees. And then in the denominator, I will have mu naught, and that's it. And the numerator is 2 pi d times g. With the exception that d, I have to be careful with it to convert it into its centimeters. So this is d, okay? So let's find d first, because we need that d in this expression, and then sub in that one in here to find it. So d is 2 times 4 times 10 to the negative 2, because we need it in meters in this expression, times sine of 6 degrees. So just to make sure I'm not doing anything crazy in here, and you correct me if I'm wrong. So I'm gonna stop sharing the screen and share with you the calculator that I have in here. Let me move this out of the way, minimize it a little. Okay. Let's stop sharing. Where is the share button? I did already stop sharing. So let me share with you. Oh, wait. Bit up and let me share. And I'm going to share the calculator actually. So the calculator in here, I need 2 times 8 and 2 times 4, which is 8, times 10 to the negative. This one actually calculator uses the same thing as you use on the by hand. Okay, in a sense, it recognizes the space as being just a. This calculator, if you look at the top, it's actually in degrees, so it's fine. So 6 degrees. So it's giving me 0.0836. How many sig figs did we say? We said 4 sig figs. I mean 3 sig figs. So it's actually in meters, 0.0820 actually. It's 8 millimeters basically separation. 36. Okay, meters. Okay, so that we need to plug it into the expression for I. For I, I'm going to sub the same value for D. So I'm going to use a trick in here, which is square root of open parentheses of open parentheses, because I'm going to do a fraction in here, of 2 times pi times d, and d is, I'm going to just copy the value from the previous step in here. Okay, that takes care of it. I know I took a lot of sig figs because d is just an intermediary value, so you're allowed to do that. You're not really required to keep just the 3 sig figs in here, okay? Times g. G is 9.80, okay? The whole thing is divided by mu naught. Mu naught is 4 times pi times 10 to the negative 7. Close the parentheses. Now close this parentheses for the division, and then multiply the whole thing by a tangent of open parentheses 6 degrees. Hopefully I didn't make any mistake. If that's the case, we should find the answer. Okay? And it's an indeterminate. And why is that? Because tangent is a negative value. Is tangent of 6 degrees an negative value or what? What is tangent of 6 degrees? No, it's positive. So where did I go wrong with this calculation? Or is it because that 10 to the negative 7? Oops. Can you guys check what I did wrong in here? So
Yeah, when I typed it into my calculator, I also got an error.
What is this thing? So let me remove the 10 to the negative 7 and just multiply it by 10 to the negative 1 and see if that's going to help. What? Okay, 2 pi over 4 pi, that is just 2 in the denominator. Okay, so let me write this expression here. What is that? Trying to understand, forget about the physics of it. I'm trying to understand what's going on in here. So 2, cancel that 2 pi. Is it? Okay, let's see here what happened. Still indeterminate. Is it the numerator? Well, that's ridiculous. Let me try to do it by hand, okay? Because that's not good. Anybody had any problems with it too, other than Martin? On the calculator? So what we have in here, we have 8 times 10 to the negative 3. So that is, let me write it again, square root of, open parentheses, of 8 times 10 to the negative 3, 8.4 actually, 8.36 times 10 to the negative 3. Okay, that takes care of that. Times 9.8, which is really 10, divided by 2 times 10 to the negative 7. I mean, this calculator should take care of these things in here. Okay. And the whole thing is times the tangent. Okay, let me open the parentheses in here. Times the tangent of 6 and close the parentheses of everything now for the entire thing. Okay. That is ridiculous. So 10 to the negative 3 and 10 to the negative 7, that's 10 to the positive 4. Okay, how about square root of? Square root of 9 times 8. That's, or 10 times 8, that's 80. 80 divided by 2, that is 40. So square root of tangent of 6 degrees. That is the problem that is causing things. And why is that? Tangent of 6 is this much. Okay, how about square root of, open parentheses, the tangent, which is this much. Okay, so let's try the expression basically without the tangent and just sub the value of it in here explicitly, because for some reason this calculator is having a problem with that tangent. So I'm just going to remove that tangent.
Yeah, mine won't let me square root the tangent also.
Okay, how about this one now? Now I'm getting a number in here. Okay. 207.5 amps, okay? Calculate the tangent by itself. That is weird. It's not an indefinite angle. So what I did now, all I did is the same expression, except that I use the intermediate value of the tangent. That's it. So the same expression, the first one that they gave us in nonsense stuff. Do we have another calculator in here? No, it's not handy. I don't have another calculator handy. So anyway, let me stop sharing that screen because I know the answer now. It says 208 basically amps because we have 3 sig figs. Okay. And let me find where the other screen is. Share. This one. So now it's saying the current is 200 amps. I mean, I know the current will be high because even for this much in here, Okay, 6 degrees is a small number, so its tangent must be a very tiny number. So that's expected. And so the current in here should be 208 amps. That's a lot of current. Okay, that is a lot of current. So we did not make any we did not make any approximation or anything like that. We made sure D is a very tiny number. Actually, it turns out to be a small number. And did I calculate it correctly in here? D, yeah, it's just 2 times the hypotenuse times the sine, because it's the opposite to the sine, 6 degrees. So this is correct. 8 millimeter separation between the wires. Just that my tiny separation.
Shouldn't it just be 0.08?
Is it 0.08 or 0.008?
If you have 8 centimeters, wouldn't it be?
No, this is 8 millimeter.
Oh, I might have read it wrong.
Yeah, it's 2. This is 4 centimeters, correct? Okay, but I need it actually in meters because we have everything in SI in here. This is in SI, G is in SI, so we have to have it actually in meters now. That's why the conversion.
Oh, I see.
Meters. So the answer was a fraction of that. So it was 8 millimeters, which is even for this tiny, and that's where the discussion is this number is a big number, okay? And it is expected this way because of the fact that the magnetic force is a weak force. So if you really want to have a huge effect, you really have to have a lot of current. Otherwise, it cannot even overcome the force of gravity, which is a negligible quantity now because the linear mass, if you noticed, oh, I know now. I'm sorry about that. That's a mistake. I hope you guys caught it. What happened to mu? So I know the current is going to be big, but I'm surprised that it's too big actually. So we need a mu there. Okay, so we need to go back into the drawing board basically and try to fix that. So we need to multiply it by mu, and mu is equal to so I got caught up in that stupid mistake. I'm sorry about it. That I forgot to something very important in the problem, which is the linear mass of the string. Okay, so it's a lot better than this value. So it's only 24 amps or 23.2 amps. And that's still too much high. It's still too big, by the way. 23.2 amps. It's still a big value. So you see how when you discuss your problem, when you check your work, it really helps a lot, because that last step, I know I don't grade on it in the exam because you're constrained with the exam and pressure and all of that, but you always have to have that in your mind. 208 amps is I mean, I was expecting a lot of current to begin with, but honestly, 200 amps is a huge current. Okay, it's a lot of current to run through a wire, and probably you're going to see sparks next to the wires themselves. Okay, flying over each way because there's too much current flying through. 23 amps also is a huge current going through those wires. And you need that much a huge current to even make this tiny separation of 8 millimeter between the two wires. The 8 millimeter is a separation between the two, okay? Remember, a millimeter is about the size of the hair. So this is 8 pieces of hair lined up one next to the other. That is how far apart they are, okay? So for that, you need this much current flowing through them. Okay, it's probably you're better off to have them both encapsulated, excuse me, in some sort of an insulating material and tight it throughout and run them through. Okay, so hopefully, I mean, look, I enjoy it when I make mistakes, honestly, because it becomes a learning curve for you guys to see, first of all, that the error is humans and everybody can make mistakes. And whoever tells you I don't make mistakes or make it look like they don't, they're lying to you, because the smartest people, okay, in the world, they tell you we make mistakes. So if you want to really be one of them, you have to do that. So I strive to be one of them. I'm hoping at least to be someday considered smart enough to make mistakes. So I'm hoping that you guys saw that too. And that is actually something you learn a lot from it. When you make a mistake, it is a valuable step. When you do the last step in the calculation to check your work and actually go back and retrace and find the error. And here it was clearly an error, an algebraic error in here. When we multiplied by 2 pi d and g, there was a mu there, the linear mass. So we needed it in there. And that would have tamed the answer a little because mu is a very small number. So the square root of a small number is still small and makes the answer a little bit more within grasp. Okay. So this is the current needed for this problem. I don't know what the rest of the questions are. No, that's it. That's problem 2, problem 61, that is. Okay. Okay, let me minimize the calculator a little bit. Problem 62. Problem 62 basically gives you this shape. Let me read through it again. The wire semicircles shown in the figure have radii A and B. Calculate the net magnetic field and the direction that the current in the wires produce at point P, which is right smack in the middle. Okay, so what I have in here, I have a semicircle of radius A, and I have a semicircle of radius B, and they're connected in here. And I have a current that is going in the inner one counterclockwise, and the outer one is clockwise. And in here, it's flowing this way. So the whole current is actually going clockwise in this inside surface in here. Okay, it's clockwise. But looking at it from here, this current is actually going counterclockwise. So the magnetic field that that portion will create will come out of the screen. So this radius A, I'm going to call it BA. BA will be coming out of the screen. This portion of the wire will produce a magnetic field in the same point that is actually going into the screen, because the current is going into the screen. I'm sorry, the circulation is clockwise, so the magnetic field is going into the screen. The circulation of the current is clockwise, so the magnetic field is going into the screen. So the second one in here, which I'm going to call BB, which I'm going to draw in red, is going into the screen actually. And then the magnetic field will be the sum of these two. Why wouldn't I include this one? Well, this one would be 0. The contribution of this one is 0, and the contribution of that one is 0. Because the direction from any element in here to the point where we're finding it, so it's going to involve DL crossed with R hat. And R hat is in this direction, and DL in the same direction. So these two vectors are parallel to one another. So it's going to involve the product of DL times 1, because the length of the unit vector is 1, times the sine of the angle of two parallel vectors is going to be 0. The sine of 0 is 0. So this whole contribution from this side is 0. Now from this one, it's going to be a negative 0, basically. That's all. So in other words, the DL is in this direction, and the R hat is going to be in this direction. So it's going to be, again, DL times 1 times the sine of 180 degrees, because they're making 180 degrees between them. And that too is a 0, albeit it's a negative 0, but there's 0. So the contribution from these two segments is 0. So the only contribution that is going to be is from the other ones. And it can go back to find what the contribution from a full circle is and divide that by half, because I am only half of the circle. So we did that yesterday, last time. Here it is, okay? So the contribution of the magnetic field smack in the middle, though, where x is equal to 0, was equal to mu naught I over 2r. But that is for a full circle. We're not doing a full circle now. We're doing half of that. So it's going to be mu naught I divided by 4r, where r is the distance or the radius of that circle. So it's going to be a for little a, and it's going to be b for big B. So that is basically the results that we're going to use from that this chapter. So again, so BA, so BA is going to be simply mu naught I over 2 times A times 1/2. The reason why it's 1/2 because it's a half circle, half loop, basically. That's all. That's all. Okay. And for B, it's going to be BB. The magnitude of that is going to be mu naught times I divided by 2B times 1/2 also for the same reason, because both of them are actually half loops. Now, having said that, the current is the same current, I. If you look at the problem, the same current flowing through the entire, basically, loop, which is in this weird shape, okay? But then A is less than B, which means that BA is more than BB. Because when you divide by a smaller number, you're going to end up with a higher number. Whether you're going to end up with the inverse of a smaller number is greater than the inverse of the bigger number. Because if A is half what B is, so this will be twice as much as the other one is. Everything else is the same. But one of them is coming out of the screen, and the other one is going into the screen. So one of them is positive, the other one is negative. That's all. So the actual magnetic field now is going to be B is going to be BA plus 0 minus BB minus 0. Or I should say minus 0 here and plus 0 there. It doesn't matter. It's 0 anyway. So this region is 0. This region is finite. This region is 0. And this region is the two values that I was talking about. BA is mu naught I over 4A minus BB, which is mu naught I over 4B. And that's the answer to the question. And it's out of the screen. Or the paper, if you're looking at the paper, okay? Coming out. Because A is bigger than B. As a matter of fact, you can do the common denominator, and the common denominator is 4A times B, and this is mu naught I times B minus A, okay? B is greater than A, so the common denominator is correct. So everything is, so it's positive coming out of the screen, okay? Does this make sense to you guys? Yes? Okay, very good. Okay, very good. So let's look at problem, the third problem that I thought, the third or the fourth? I lost track of the numbers. I think it's the fourth. So it's problem 67. Problem 67 requires some work in here. Not that the others did not. So problem 67, a long straight cylinder oriented with its axis in the z direction carries a current whose current density is J. So we have a cylinder along the z direction. Oh no, that's actually not along the z direction. Here it is. Okay. And it's a long one. And it has a current density J. So the current density J in it. Okay. And J is pointing for the direction of where the current is pointing. Okay. So if this is K hat direction, J is a vector, which is something that we saw a long time ago. It's given by 2 I naught divided by pi a squared times 1 minus r over a squared k hat. So it has this expression that depends on r, where r is this distance basically. So let me redraw the shape in here. I'm gonna make a mathematical cut in this wire. This is how the wire looks like when I make the cut through it. Okay. So the current changes with r. So r is equal from 0 to a, where a is the diameter of this cylinder. So in this case, J has this symmetrical property. K hat is coming out of the screen. Okay, K hat is coming out of the screen. And r is a distance from the center of the cylinder up to some point. At that point, J in magnitude will be equal to this expression that they gave us, 2I naught over pi a squared times open parentheses 1 minus open parentheses r over a squared, and that is basically the magnitude of the current density. So it depends on how far you are. If r is equal to 0, it's 2I naught divided by pi a squared in the middle. And as r starts to increase, it drops quadratically. When r is equal to a, this becomes 0. So the current starts from some value and drops to 0 in a quadratic fashion, that's all. So if I try to plot this function as a function of r, of course, r is positive in here. So it's gonna start from a finite value and drops in a quadratic fashion. At some points, it's gonna be 0 in here, okay? That is basically what this thing is. So this is r is equal to a in here. At this point, the current is 0. Otherwise, it's quadratic, as you can clearly see in r over a, okay? For r greater than a is equal to 0, that's what they say. I mean, there is no current outside of the wire. That is the current density. That is the current per unit area, okay? Where a is the, r is the, show that I naught is the current passing through the entire cross section. So basically, what they're saying in here is the entire current, let me use a different color, it's shaded gray in here. This current through the entire cross section is I naught. That is the first question. So for that, we're gonna sum through this current density from the beginning to the end of the area. So basically we have to sum JDA. So the current I is the integral through this surface of JDA. But because the surface has this circular symmetry, I'm going to take advantage of that and write dA in the following fashion. First of all, as you can clearly see, J is in the k hat direction, and A also is in the k hat direction. So these two vectors are parallel to one another. So I'm going to write it as just the integral of the surface. Don't be afraid of this double symbol in here, because we're not going to do it actually. We're going to do just a single integral, okay? Because of this radial symmetry. This thing has a radial symmetry. There is no theta in it, so we're not going to worry about theta. So theta is just going to be the pi that is needed to complete the whole thing. Okay, the 2 pi basically. So this is how I'm going to take this area now. I'm going to look at it this way. At a distance r and r plus dr. So this is a distance from the center, and this is a distance r plus dr. So what I'm going to do, I'm going to take this strip and open it. If I take this strip and open it and cut it in here, for example, this is how it looks like. It has a width of dr, this width dr, but it has a length of 2 pi r. So it's 2 pi r dr. So this area then, the strip that I took, what is its area? It should be width times height. So the dA then should be simply 2 pi r times dr. So this area dA then becomes, and the integration for r goes from 0 to a. That's all. So we're going to make just a single integration in here. So if we do that, the total current then will be equal to the integral from 0 to a of g times this area, and this area is 2 pi r dr. Okay. And now we have the value of the current density, which is this constant 2I naught over pi I squared times this function, this quadratic function in R. So basically what we will have in the end is the following. 2I naught over pi A squared times the integral from 0 to A of 2 pi R times 1 minus R over A squared times dr. The 2 pi and the pi cancel, and I will have a 4 in the numerator from the other two. Okay, that's all. So I will have a 4 I naught over A squared times the integral from 0 to A of R times 1 is R minus R cubed over A squared dr. Okay. I know some of you are probably remembering what we did when we had the current, when we had the charge density and the volume, and we did the integration and all of that, and we took advantage of that R over A and or R over big R in that case, and we divided, we called the new change of variable, and we did the integration. We could do the same thing in here, but actually this integration is simple. So the first integration is the integral of x dx, and the second integral is x cubed over dx. Okay, that constant is just a constant in here, which we're going to do. So what is this integral of x dx? If you guys remember from your calc classes, the first term,
X squared over 2.
very good. Don't forget the boundaries of integration from 0 to A. And the second one is, first of all, I have that minus and 1a over a squared, and the x cubed should be x to the power 4 over 4 from 0 to a. Okay. So the first value is going to be a squared over 2. So the first value is going to be a squared over 2. And the second value is going to be, first of all, I have 1 minus over a squared times a to the power 4 over 4. And again, a squared and the 4 cancel, and we'll be left with an a squared. So what I have in here, and I have an a squared over 2 minus a squared over 4, and the common denominator is 4. So it's going to be basically a squared over 4. So a squared over 4, and I have an 4 over a squared. So the answer at the end will be basically 4 I naught over a squared times a squared over 4. And the 4 cancels the 4, and the squared cancels squared. And that is exactly what we were supposed to show, that the total current is I naught. That is the question. That is how we were asked to do that. First part, show that I naught is the total current passing through the entire cross-section of the wire. So part B, using Ampere's law, derive an expression for the magnitude of the magnetic field B in a region greater than A. So now we need to find the magnetic field outside of this wire. Here, somewhere outside here. For that, we're going to take a path for the magnetic field, which is going to be a circular path, and we're going to calculate its circulation using Ampere's law. So part B, Ampere's law, said that the circulation of the magnetic field over any closed path, for that we're going to take a circle for our case, okay? Because it's easier to do a circle, is equal to mu naught I. And the mu naught I enclosed is just this value that we calculated right now. The current enclosed is just in this one. And it's coming out of the screen in here because the J hat is coming out of the screen. So the circulation is in the positive direction and the magnetic field is in the positive direction. So the dot product in here will simply be B times dl. But P now, by arguments of symmetry, should be the same. So when you do Ampere's law, you have to choose an Amperian loop. So I chose a circle. So the first step is in here, choose an Amperian. And like what we did in the Gauss's law, we had to choose a Gaussian surface. Here, you choose an Amperian loop of your own choosing, depending on the symmetry of the problem. Because the problem has this cylindrical symmetry, I choose a circle because of that cylindrical symmetry. Because if I spin the wire one way or the other, the current density does not change at all, because it depends only on R. It doesn't depend on the angle theta at all. So if I spin it one way or the other, it doesn't change. Therefore, I expect the magnetic field to be the same value at any distance r greater than or equal to a. As long as I'm on same distance, as long as I'm on same circle. And it chose the Amperian loop to be a circle for that purpose. So choose an Amperian loop by the symmetry in the problem. And this problem has cylindrical symmetry. That's how we do it in here. Okay, similar to what we did in there. So B will be constant. Not only is going to be constant, but also parallel to DL. So it's going to come out of the integral. So the only thing that I'm left with is integrate DL basically from 0 to 2 pi r. 0 to 2 pi r. Okay, because that's the circumference of the circle whose radius is r. So this is radius r. Okay, because I want to find the magnetic field in that point, is equal to mu naught times I naught in here. And that is the value that we just calculated. The current enclosed is mu naught, is I naught. So this is 2 pi r. And this is B is equal to mu naught I naught. And from here, you're going to find the magnetic field in any region outside of the cylinder is given by this expression. So that answers that question, provided R is bigger than or equal to A. Okay. So the same thing that we did actually when we were applying Gauss's law. We chose a Gaussian surface and we determined its properties if it does not have any built-in native properties already. Based on that, we were able to find the answer. Anything we added to the Gaussian surface, basically anything, because the entire surface is fictitious surface, any properties we added should not be part of the final answer, as that is just made up stuff. Same thing with the Amperian loop. The Amperian loop is your choosing, usually chosen by the symmetry in the problem, and then whatever stuff you added to it should not be part of the answer. The only thing we added in here was actually the radius of the Amperian loop, and that is part of the problem. That is where we want to find the magnetic field. So that should not matter in this case. It should be probably part of the answer, and it is. Okay, so that is not something we should be worried about. Had we introduced a new parameter, for example, for the Amperian loop, then and we found the answer depends on that parameters, then we have a disaster before us because that should not be the case. Okay, so that is something that you guys have to be aware of when you're doing this problems. The steps are similar to what we do in Gaussian surfaces with Gauss's law, except there we were dealing with surfaces, and in here we're dealing with path integrals, with basically loops. Okay, so this is the usefulness of this problem. So, and usually when they ask this question, the next question is to find the Gauss's law. So, and then part C, obtain an expression for the current I contained in a circular cross-section of radius r less than or equal to A. So because we're headed there. So the second part in here, what we're doing on time, man, we still have this about 10 minutes and we have quite a few things to cover. So probably we're going to skip the last problem because I left it to, it's a good problem too. So let me draw a better surface than this one in here. So let me draw. So this is a cut from the cylinder. So this is somewhere in here is the center. Okay. So I'm going to take a Gaussian surface now again. That is also also a, I'm sorry, this is we're trying to find the current at this point, so it doesn't matter. Control Z, what are I doing here? I wanted this surface in here, Control C, Control V. I want to make it slightly bigger. So again, this is the strip I was talking about earlier. This is the same fashion. So again, we came in here at a distance r from the first one, and we went to a distance r plus delta r. So this is r plus delta r. Okay, and they come with a cut in here and see how much current is enclosed in here first. So this one will be the current density times the area dA. And the area dA for the same thing, if I cut it in here and open it, it's going to be of a very long length, which is 2 pi times the radius in here. This is the circumference of the circle. And of width dr. So the area dA will be simply 2 pi r dr. And then I'm going to change r from 0 to r only, because they told us inside. So I'm not going to integrate from 0 to a big A, but I'm going to little a, but instead I'm going to integrate from 0 to r. So I'm going to change the variables in here. So I'm going to call this variable r prime. R prime changes from 0 to r. That's it. Because they tell us to find the current enclosed in somewhere in the area inside. So we want to find I actually now here enclosed in this area only. And this, yes, okay, enclosed in this area. So it's going to be J times dA integrated from 0 to R. Okay. So this current I for R, for any R less than A, this is any R less than A, okay, is going to be equal to the sum from 0 to R of the current density times 2 pi R prime dr prime. And J has this expression again, which is equal to 2I naught over pi A squared times 1 minus R prime now divided by A squared. Because the variable now that is changing is R prime from 0 to A, from 0 to R. Okay. So now we're going to do the same steps as before. The only thing is the boundaries of integration now, instead of going from 0 to A, they will be simply from 0 to R. That's all. So the answer should be identical to the previous steps, except at the end, I, now which is a function of R now, is going to be equal to 2 pi, 2I naught, I'm sorry. And there was some cancellations because of that. So let me, so the front of it was 4I naught divided by A squared. So it's 4I naught divided by A squared. So it's not 2, 4 A squared times, again, it's X squared or R prime squared in this case, we call it R prime, squared over A squared, integration from, is it A squared? No, it's simply A squared. Sorry, there is no R squared, that's all. There is no A squared in the denominator. So there is no such a thing in here. I'm sorry about that. I'm just trying to save time in here, just instead of repeating the whole thing, because we have A squared already outside. So this part is just R prime. When you multiply, when you integrate, it's going to be R prime over 2. So it's going to be over 2 integrated from 0 to R minus the other value has now an A squared in the denominator. The second one has a 1 over A squared times R prime squared divided by 4, R prime to the power 4 divided by 4. So it's minus 1 over A squared times R prime to the power 4 divided by 4 integrated between 0 and R. Again, the lower limit is 0 because when you sub 0, 0, the upper limit is going to be R squared, then it's going to be R to the power 4 in here. So what we have in here is I as a function of R will simply be equal to 4I naught divided by A squared, open parentheses, is going to be R squared over 2 minus R to the power 4 over 4A squared. So this is the expression for the current at any distance R from, that is from the center of the cylinder, okay? We're going to apply Gauss's law. We still have about 5 minutes, 6 minutes left. And we're meeting later on, by the way, for the lab. So what we have in here, we have we're going to do the same thing. We're going to choose a Gaussian surface that is actually a circle of radius R. We're going to choose an Amperian loop, which is a circle of radius R less than or equal to A while we're inside. And by symmetry, we're going to make the same argument as before. So the first side of the circulation, which is this one, BDL, is simply going to be B, the integral from 0 to R now, you have to be careful in here, of 2 pi R prime, 2 pi, I'm sorry, 2 pi R of simply DL, I'm sorry, of DL. And that is going to be 2 pi R. On the other side, it's going to be mu naught times this current, which is a function of R that we just found. Because the current enclosed will be this whole thing. So if we're careful enough with the calculation, please check this calculation again, okay? That's part of your job in here. Is that B times 2 pi R, that is on one side. The whole purpose of Gauss's law and the whole purpose of Ampere's law is so that you don't really do the integral, at least on this side. And the other one should be an easier integral. I mean, I know it looks like it's a little bit complicated, but it's just the integral of x dx and the integral of x cubed dx. So this is not hard enough for you guys to do on this level. So it's 4 I naught over a squared times open parentheses r squared minus over 2. I should really have gotten rid of that 2 because I have a 4 in here. Okay, over 2 minus r to the power 4 over 4 a squared. Okay, now we should fix this issue as well. First of all, this 2 and this 2 and this 2 will be living in here 2 and here 2, and this 2 and this 2 is gone. So that takes care of all of the numbers in the problem except of this one. And then this r and this r squared and this r to the power 4 will be left with an r in here. And then I have a pi in the denominator. So the final expression in here for b is going to be equal to, first of all, I'm left with an I naught in the numerator divided by pi times a squared. And I have an r in here that I'm going to pull out too, because I will be left with an r in here and one of these powers in here. So I'm going to take it out, times open parentheses. I'll be left with nothing in here except 1, minus, I had an r cubed now, since I took another r in here, so I'm left with an r squared over 2a squared. And this is the expression of the magnetic field inside that cylinder at any distance from the center. Note that it is 0 at the center, smack in the center. But smack in the center, there is no charges enclosed. So it's expected the magnetic field will be 0. And it starts to grow until it, or actually starts to change, because at some point it's going to be positive at the end, okay? So this is basically how the magnetic field is inside using Gauss's law. Unfortunately, there is not much time to really do the problem 2849, but I'm going to tell you roughly how that is. So the last problem from this chapter is problem 49. So what problem 49 says is the following. You have two currents. So we still have about 3 minutes, and I know we're meeting later on, okay? So we have a current that is going into the screen. No, I'm sorry. What am I talking about? There's no current. We have charges, actually. We have a charge moving in this direction, V, and we have a negative charge. So this is the y-axis, and this is the x-axis. And we have a negative charge moving in this direction with another velocity v prime, okay? And they gave us this distance, which is 30 centimeters, and they gave us this distance, which is 40 centimeters. And so we use the Pythagorean theorem to use the square root of 9 plus 16 is 25. So this is 50 centimeters, okay, if we really want to find it. And they gave you the value for V, they gave you the value for V prime, they give you the charge Q, and they give you the charge Q prime, but Q prime is negative, okay? And they want you to find the magnetic field inside in the origin, in this point. For that, you're going to use the expression QV cross r hat divided by the distance squared. And don't forget, we have mu naught over 4 pi in here. This is the magnetic field created by any given charge. The V in here is along the x-axis for the positive charge. And the r hat is actually in the negative j hat direction. And the magnetic field is going to be, in this case, in the positive direction, okay? No, I'm sorry, it's in the negative direction. You can just do the cross product, okay? Because you have everything. You have V, which is some number, which they gave you in the problem, in the I hat direction. And you have R hat, which is actually equal to negative J hat direction, because this is what J hat is, okay? So you're gonna form the cross product of I hat cross with negative J hat, and this should be equal to negative K hat, okay? For this one, and Q is positive, so nothing changes for this one. But the other one, you have to be very careful. V prime actually is V prime in the j hat direction. And now this vector is actually the r hat is actually in the negative I hat direction. Okay, so you're going to form j hat crossed with negative I hat. This j hat crossed with I hat is actually this one, and this one is actually negative k hat. Times a negative becomes a positive, times another negative coming from the charge, because this charge is negative. So it's going to be a negative times negative times negative. So at the end is going to be a negative. So it's 2 is going to be a negative k hat. There are 3 negatives. One of them is coming from the direction of this r hat. And the other negative is coming from the cross product of j hat with I hat. Because you know I hat j hat is equal to k hat. Then j hat I hat should be negative k hat. So there is a negative coming from the cross product. And there is a third negative coming from the charge itself, because all of this involves the charge. So both magnetic field will be pointing in the negative k hat direction. Both of them will be in the same direction. You add them up in the origin. And then they tell you to find the force on one. I know I'm 1 minute outside of the time. So basically, you calculate the magnetic field in this point, for example, due to this charge. This is a direction now of r hat that you need to find. Okay, you know the velocity is in the x direction. So this component of the r hat is not going to contribute because it's involved the sine of 180 degrees, which is 0. It's this component that matters for r hat, and you're going to find the force exerted in that, because you have already B in that point. So you have B in that point, B in where Q positive is. You can use this calculation to find it. Once you find it, you're going to use QV cross B to find the force on this positive charge, okay, due to the negative one. And this is basically how we're going to solve this problem. I expect you guys to finish it. If you have difficulty with it, please let me know, and I should share a solution with you. It should not be hard to understand once you see all of the crosses and everything else. That is a difficulty with this entire chapters. Okay, I'm 2 minutes outside of the time. I'm sorry for that. So let me stop sharing the screen. And we're meeting later on today in about actually a little over half an hour for the lab. Okay, so I'm going to stop sharing the screen.